We're going to take a look at a specific type of rate of change question, that being exponential growth and decay. We're going to start off with a very simplified model. And the basic assumption is growth and decay is proportional to the population. So the idea being the greater the population, the greater the growth, the smaller the population, the smaller the growth. But you could similarly say the greater the population, the greater the decay, so more people would die. The smaller the population, the smaller the decay or the death. So in other words, the P to T is directly proportional. Well, that means it's equal to some constant times the population. So the P to T is equal to the K times P. Now, the solution to this differential equation at this stage, we can't do. We will later on work out how to solve this type of differential equation, well, next year. But for now, all we need to know is the solution to this differential equation is this. P is equal to AE to the KT. Now, what do all those variables mean? P is the population at any given time. A, I'm using to represent what the initial population, so what it is at the start of the problem. And K would be our growth or decay, depending on whether the population is growing or dying, constant. And T represents time. So I'm going to prove it, which is the best I can do at this stage. So if I know this is a solution, I can prove that it satisfies this differential equation. If P is equal to AE to the KT, we'll differentiate the exponential. We differentiate the power. The power is KT. Differentiate KT, we get K. So I get KA e to the KT. Well, yes, indeed, that is K times what we said the population is. So it does satisfy that differential equation. So as I say, at this stage, all we can do is show that the solution works. Next year, we'll actually work out how you can derive it. First example, we've got some bacteria that's hanging around and it's growing at a rate of 10% of the population. So that's its growth rate per hour. Initially, we have a population of 1 million. At this stage, standard sort of problem would give you the solution and say, look, show that it works. And so that's what we're doing here. Show that P equals AE to the 0.1t is a solution to our differential equation. And you might be saying, well, hang on, what differential equation? They didn't give me one. Well, they didn't write it out specifically, but it's there in the question. They said the growth rate per hour is 10% of the population. Here's the solution that they gave us. Let's differentiate it and find the P to T. Differentiate 0.1t, you get 0.1. So we have 0.1 AE to the 0.1t, or AE to the 0.1t is P, so we end up with 0.1p, which is 10% of the population. So yes, this is a solution to our differential equation. Determine the population after 3.5 hours. So how much has this grown? So we've got to work out, first of all, what the equation actually is, because at this stage we have AE to the 0.1t. That's fairly simple because A, remember, was the initial population. But if you didn't spot that, you could say, well, I know that T equals 0, P is 1 million. Well, therefore, A has got to be 1 million. So P is 1 million E to the 0.1t. Now, we want to know after 3.5 hours. So we simply now substitute in 3.5 into our equation, and we get 1,419,000. So that's what we've got after 3.5 hours. Let's do one where it's decaying rather than growing. So we've got an island. A long time ago now, 1960, the population was 1,732. But something must be happening on this island because the population is dying out. In 1970, it's 1,260. So they've said find the annual growth rate. Well, we can see in reality it's going to be a decay rate, but we can still call it a growth rate. It'll just be a negative growth rate. So we're assuming the P to T is equal to KP. So from there, I'm allowed to say, well, I know the solution to this will be P equals AE to the KT. I don't actually have to go and find that solution. Remember, at this stage, we can assume that is the solution. Let's find A, the initial population, was 1,732. So there's A. So our equation, 1,732 e to the kt. We want to find k, the growth rate. Well, the other piece of information is that after 10 years, the population is 1,260. So let's sub that in. We've got an exponential equation to solve. We need to make k the subject. So we'll divide by 1,732, log both sides, and divide by 10. There's an exact value, but they've said to the nearest percentage. So if I calculate that out, that's minus 0.0318, etc. So to the nearest percentage, my growth rate is minus 3%. So how long will it take? In how many years will that population be half? Well, half of the initial population is 866. So that's what we're basically saying. When is p equal to 866? Again, sub into the equation that we've worked out, and we've got e to the kt is half. Once again, we've got to make, in this case, we've got to make t the subject. So log both sides, I get that kt is log of a half. T is equal to 1 on k log of a half. The t works out to be 21.786. K is that number that we worked out in the last question. Don't use the negative 3%. That was just an approximation. Use the exact value. So in 22 years, the population is halved. This brings up an interesting point. Had that worked out to be 21.2, and they said in how many years will the population be halved, I would still say in 22 years. Because at 21 years, it hasn't halved yet. At 21.2, it halves. So I'd say after 22 years. Now, when it comes to solving these problems, make sure you write down the step that I've got there, the t equals 21.786. So if you do write down 21 instead of 22 or something like that, as long as you can justify your answer, it's going to be fine. They mainly want to see that you can calculate it out. So the key thing here really is the 21.786. All right, a handful of growth and decay questions to have a go at.